After the introduction Roman gave last time, we will now start with the actual mathematical course, and I will introduce singular homology today. So let me fix the title, singular homology. And before I forget, I should also fix a topological space, which will be at the center of our considerations today. So fix a topological space and call it X. And as Roman already mentioned last time, the basic building blocks for singular homology is the simplices. So we should give a mathematical definition of them. The n-dimensional simplex. Oh, I think we should adhere to our previous idea of writing definitions in green. The n-dimensional simplex is the following set. So it's denoted by capital delta with upper index n. And it's formed by all the elements of the vector space R to the n plus 1. So note the shift in dimension. The n simplex is a subset by definition of R to the n plus 1. And it's formed by those elements whose sum of coordinates is equal to 1. So since I'm in R to the n plus 1, I need n plus 1 coordinates. So I better start counting at 0 and n counting at n. That's the first definition. And the second definition is that I want all those coordinates to be non-negative. Okay. And yet another notation for the same object is the following one, which will be particularly convenient for working with later on. We write bracket v0, v1, and then all those coordinates here. And how you should think about this notation is these elements vi are just the standard basis of R to the n plus 1. And this tuple denotes the convex hull of these points in R to the n plus 1. And they are called vi because the v is for vertex, because it so turns out that those elements will just be the vertices of this simplex. So maybe better than 1,000 words is a picture. Let us just look at what the simplex looks like in the various dimensions. So if we start with n equal to 0, in this case the vector space of our consideration is R. Yeah? R to the n plus 1 is just R1 then. Let me write the 0 element here. And in this case the condition we have to deal with just means that the only coordinate that exists must be equal to 1. So in fact, in this case, the 0 simplex is just this point sitting at 1 here. Yeah? A 0 simplex is just a point. For n equal to 1, what happens now is that we have to consider the vector space R to the 2. So we should draw a coordinate axis in 2 coordinate axes. And in this case, we've got the 1 here and the 1 here. And the elements in R to the 2, which have non-negative coordinates, who sum up to 1, these lie precisely on the line connecting these 2 points here. Yeah? So in this case, the 1 simplex will just be a straight line. The next case to consider would be n equal to 2. In this case, we're dealing with R to the 3, so I should draw 3 coordinate axes. And again, I write down the coordinate 1 at each of them. And now the elements with non-negative entries who sum up to 1, these are all the ones sitting on the triangle here, which is formed by these 3 points, the points given by the standard basis of R to the 3. So just to give you an idea, I'm going to draw some straight lines here. So the triangle sitting in this orthant here, this is precisely the 3 simplex. The 2 simplex, I'm sorry. 2 simplex in R to the 3. Okay, and maybe final picture would be the case n equal to 3. So in this case, I of course can't draw r to the 4 anymore, but I can still give you an idea of the shape of the 3 simplex that comes out, because in this case, this will just be a regular tetrahedron. So let's see if I can draw this. Take a regular triangle here, and then there's a point farther in the back, and I connect it like this. And then the last line is in the back, so I'm going to dash it to allude to the case that it's far behind. Yeah, so this should be, I think, an okay picture. So that's the 3 simplex, and these simplices are now used to define what's called the nth singular chain group. And to do this, now that we've seen something very concrete, I'm going to say something abstract, yeah, in good reference to our previous course. There we had considered categories and functors, and maybe the easiest example of a functor were the forgetful functors. So let's consider one of them. Consider the forgetful functor, which takes an abelian group. So I'm not sure what notation we used for abelian groups, but maybe I'll just...
I think AB.
AB is okay? Okay. Now let's stick to it. AB. And the functor that not only forgets that it's abelian, but that forgets that it's an abelian group, that only remembers that it's a set. Yeah. And to this functor, we now consider the left adjoint. So let FA be the left adjoint. Now the message from last semester was that left adjoints to forgetful functors correspond to free constructions, and this is also explaining why I chose the letters F and A here. So F and A is for free abelian. I want to call this the free abelian group generated by a set. Yeah?
It's not necessarily true that you always have a left adjoint functor, but in that case you do have one.
Yes. And actually one can also make it concrete, and maybe I should also do this.
I was about to say it. It sounds, maybe if you haven't heard this categorical language, it still sounds scary, yeah. But it's really not a scary construction. It's a very easy construction. This
easy enough that we can just give it right now, at least on objects. So what does this functor do? The free abelian group of a set, just a set, call it S. Well, that as a set, first of all, consists just of all formal Z-linear combinations of elements in S. So let me just write it down. Sums of indexed over elements of S, and we just write artificially a coefficient in front of such an element of the set, and this coefficient now comes from the integers. Okay, so that's very reminiscent of the free vector space construction, which we did see last semester, as I recall. The only difference being that now the coefficients do not come from a field, but from the integers here. And actually, it's very suggestive now also how the group operation works. I mean, it works the way you want to do it. Yeah, you just sum two such linear combinations by distributivity and get a new one. Yeah, so this is the ordinary way you would think to deal with this. Okay, so this is the free abelian group generated by the set. And why am I telling you this? Because this is now used to define the nth singular chain group. So let me keep this maybe visible. The nth singular chain group is now the following. So it's denoted Cn, so C for chain, and to make reference to the word singular, I might once in a while write sing as an upper index, but I might also be sloppy and lazy and leave it out at a later point. But right now let's put it down. So Cn sing of the topological space X we have fixed in the beginning is given by the free abelian group of the set of all mappings now, call them sigma n, of the n simplex into X. Only requiring that they be continuous. Sigma n is continuous. Okay, that's the only thing where the topology enters. We require these maps here to be continuous. Okay, so this of course is a huge free abelian group. Yeah, I mean there are, depending on X, there are a lot of mappings of simplices into the space. So right now this is just a huge free abelian group, typically with uncountable rank. And that of course is also not yet the definition of homology. So let's first of all fix some terminology to carry on. So first thing we should say is that such a map, the whole map sigma n from delta n to the X, is called a singular simplex.
Why is it called singular?
Yes, I'm going to explain this in a moment. It's called a is not yet the definition. A singular, and if we want to refer to the dimension, we can also say it's singular n simplex.
Not to be pedantic, but if
yes.
you do definitions in green, then you should also do the singular chain group in green.
Ah, that's true. But let me see if I can still adjust that. All right. So was this the style button? Maybe.
No, the left one.
No, this one, right?
Ah, this one, yeah.
Yeah. Okay, thanks.
Okay.
So the n singular chain group is this one, and just a map sigma n from delta n to X is called a singular n simplex. And now Roman asked the question, why is it called singular? Well, this refers to the fact that we are only requiring the map is continuous. And as you know, continuous maps can be very irregular, very singular. This is the point here. So let's just maybe draw a suggestive example. So let's say we've got our simplex. Let's draw a 2 simplex here. And here we've got our topological space, X. And now we have our map, sigma n, which I just illustrate by drawing its image. And then it might look something like this. So I've got here this triangle which might be squeezed in the middle to a point and then gets back out again. So for example, something like this could be the image of such a map. Yeah? So I squeeze this triangle here in the middle and put it in so that there's a singularity sort of in the middle of the triangle. And of course this is allowed because this is a singular map. This is a continuous map. Yeah? So this does not in any way not obey the definition. It's totally fine. Yeah? So these singularities is what explains the terminology. Okay, and by the way, it's also of course not required that this map is an embedding or so. It doesn't have to be injective, right? It can look like this. Okay, so this is why it's called singular. And what else shall I tell you about this? Okay, yeah, if I've said that such a lonely element is, such a sigma n is called a simplex, I should also tell you what we call such a formal linear combination. So an element of the chain group of Cn sing X is then called a singular n chain. Yeah, so the formal linear combinations describe chains of singular simplices, a singular n chain. And the reason behind this is that, well, this picture that Roman already announced mentioned last time was in the case that n equals 1, then he was considering like chains of those simplices. Yeah? So this would, for example, be such a chain. Though right now, a chain doesn't really have to look like a chain in this picture. It might be anything. Yeah? So any formal linear combination would likewise be a chain, but it so turns out that the chains that we look like chains will be particularly important. So maybe this just as a remark for what we will explain in a moment. And the next remark I want to give is that actually, as we defined it, the chain group is a functor from topological spaces to abelian groups. And here the situation is a little bit better as in the case of the fundamental group, because it really is a functor from topological spaces, not from pointed topological spaces. So Cn sing, where we leave the variable blank, is a functor. Well, it was defined by a functor, so it's not very surprising. I'll say in a minute what it means. Cn sing is a functor from the category of topological spaces to the category of abelian groups. And now what does it mean to be a functor? It means that if you have a morphism in the category of topological groups, so a continuous map from spaces x to y, then this thing is mapped by our functor to a morphism of chain groups. So that's going from Cn sign x to Cn sign y. And we should, of course, also now denote the morphism Cn sign f. And what does it do? Well, I here just got a free abelian group generated by singular n simplices. So to describe or to define this morphism, it's enough to say what it does on a basis. So it's enough to say what it does on one singular simplex. And it does something very easy. So sigma n is a map from the simplex to x. So I can push it forward to y just by f. So I compose it with f. Let me erase this. F circ for composition sigma n. Yeah, this is how it acts as a functor on morphisms. So here's the definition. For each n, we have a so-called boundary homomorphism. So that's the definition, should be in green. Homomorphism, which starts, well, it's denoted del n or dn, we just say, and it starts at the nth singular chain group of the topological space X, and it ends in 1 degree lower, so in the n minus first singular chain group of X. And we define it on a generating set of our free R module here. So we just say what happens to one particular singular n simplex. And now we have to come up with an n-1 chain, a singular n-1 chain. So it has to be a formal sum of n-1 simplices. So how do we get n-1 simplices out of one given n simplex? Well, we take the faces of this n simplex. So let me write it down. We map this to the sum of all its faces. And we introduce an important sign, an alternating sign before the sum. And then what do I mean when I say face? Well, I take this n simplex and I restrict it to the ith face, which means I take the convex hull of all vertices where I leave out the ith one. So I write it like this, V naught Vi hat. So this is notation I have to explain now. It means I leave out the ith vertex. And then I go to the nth vertex. And this is the ith face. So in case the simplex is a 2 simplex, then if you just take one particular simplex, the ith simplex, then the ith face would be the side of the triangle opposite to this particular ith vertex. And in case of a 3-dimensional simplex, so a tetrahedron, then you would just have some vertex, which is the ith vertex, and the ith face would be the opposite face of that tetrahedron. Yeah, so the ith vertex would be the tip, and the opposite face, well, yeah, would be the ith face.
Maybe you can draw a picture of two simplex.
Yeah, I can do that.
V0, V1, V2 with this.
Yeah, let's do that. So here I've got the two simplex, V0, V1, V2. So what happens if I leave out the, say, 0th vertex? Then I'm stuck with, or I'm left with the convex hull of the other two vertices, which would be the opposite side here, right? So this is the idea. So in this case, V0 had V1, V2. This would be this part here, right? From V2 to V1. Okay. All right. So that was a picture. At the site. And now I should say a few more words about what I really mean here. Namely, when I say I restrict the n singular simplex map from the standard simplex delta n going to the space X, and I restrict it to the ith face here, then what I really get, well, it's a restricted map defined on this face, but what I really need to come up with a singular n-1 simplex here is a map defined on the standard n-1 simplex. And this is something that's implicit in this definition. So let me write this down here, where the hat means omission. Oops. Omission. And we identify the standard n-1 simplex, delta n-1, with each side, so with V0, each face I should have said, Vi hat Vn, by the unique linear homomorphism which preserves the order of the vertices. Homomorphism which preserves the order of the vertices. So maybe I should say in words again what I mean by this. So the n-1 simplex here, this is now the convex hull of the standard basis in R to the n. So it goes from V0 to Vn-1. And how do I identify it with this simplex here? Well, I start sending V0 as the V0 in this simplex here. Where's my cursor? Here. In this simplex here to the V0 here. The first one to the first one here, and so forth, until I arrive at the gap. And in that case, well, I've got the ith vertex here, which I send to the I plus first vertex here, and then I carry on, right? And then this assignment of vertices extends uniquely, yeah, as a linear homeomorphism from delta n-1 to the ith face, right? And with this identification, I, in the end, actually do end up with a simplex in a singular n-1 simplex in X, yeah? And in this sense, this homomorphism Dn actually is well defined and ends up in the n-1st singular chain loop. Okay, so one can think about this boundary homomorphism as actually defining the boundary of a simplex. So one gets the sum of all those faces of the simplex. The only important thing is this additional sign that we introduced, and we introduced it for a reason. Namely, it effects that the following lemma is true. Namely, if I walk along two consecutive boundary homomorphisms, so first I go with delta n plus 1 from the n plus first chain group to the nth chain group, and afterwards I apply delta n from the nth chain group to the n minus first chain group, and in this case what I get is 0. So in words, the boundary of a boundary is 0. And well, if you think about it like pictorially, then maybe it's more or less clear that this should be true. So if you have a tetrahedron, you take the boundary of it, what you're left up with is the outer surface sort of this tetrahedron, yeah? This the union, if you want, of all those faces. And if you do it one more time, then sort of each of these triangles cancel out at their common side. So the new boundary will have, will be a sum of sides of triangles, but every side will occur once with the positive and once with a negative sign, so that in the end you get 0. This is sort of the geometric idea behind this lemma, but the proof is a formal computation which we should not leave out. So let's just see why this is true. Okay, so how do we do this? Well, let me just be brief and write dd. And of course, to see that the whole composition is 0, it's enough to evaluate it on one particular singular, what do I have to say here? N plus 1 simplex, I guess. And if we can show that this is 0, then of course the whole homomorphism is 0, because then all generators are mapped to 0. Okay, so actually I'm not happy with my index here. I think I want to start at n here. So I prefer to write it like this, so things will be easier to denote. Yeah. Okay, so let's start with an n simplex, and
so dn goes from the group Zn to Cn minus 1.
From Cn to Cn minus 1.
Okay.
Yes. Yes. So the index always denotes the chain group where we start.
Yeah.
Yes.
And this decoration sigma to the n, that's just to remind ourselves.
To remind it does not mean a power or something, it's just an upper index to remind ourselves that we're dealing with a map defined on the singular n simplex. Yes. It's, I think, the same notation that Hatcher uses, so I thought it would be good to adhere or to adopt it. Okay. So we just do the computation. So first step is inserting the definition. So what does it mean to take d of sigma n? Well, it means we take this sum, alternating sum of these restrictions to the faces with our identification to the standard n minus 1 simplex. So I should now put the n, vi, vn. Okay, so since this homomorphism D was defined on the generators by linear extension, I can of course just pull out this linear combination and write this like this: D of sigma n restricted to v naught vi hat vn. Okay, and now I apply the definition of the boundary homomorphism a second time. Sum I0 to n minus 1 to vi, and now I get a second sum. And now I gotta be a bit careful, because now I already have a gap here in my convex hull, and I have to be careful if the new gap that I introduce now with the new boundary homomorphism occurs before, so in front, or after, here behind the gap. So this is why I want to split up this sum in two parts, where the first part, well, now I have to introduce a new index, j, and I only sum until the gap. So I only sum until, well, do I sum until I or I minus 1? I sum until I minus 1, yeah. And then it's minus 1 to the j, and I take my simplex here. And of course, I should now iterate this construction, but I use a suggestive notation for this. I just introduced the new gap directly here in this convex hull. So now there's a new gap before the I, Vj hat. Then there's the old gap, Vi hat. And then I go until Vn. Okay, so since I only sum until I minus 1, my gap always occurs here in front of the I. So therefore, I have no trouble writing down what happens. I just have to add now the second part, namely now there's the gap, so there's nothing I can leave out. So now I resume summing at I plus 1, and I end at n. Right, and now I gotta be careful about the sign, because now the gap I want to introduce occurs behind the old gap, which means it's not at the jth place, because there is already a gap before it, so it's the j minus first place. So this is the correct sign here. And now the old gap is the first one, the new gap is the second one, and I go until Vn. Okay.
So just to say again what you basically said, if you use these two hats in the notation, then this is an n minus 2 dimensional phase of this simplex V0 to Vn. And again, we identify this with delta, with the standard n minus 2 simplex, delta n minus 2, according to the order of the vertices written here, so that we can view this restriction really as a singular n minus 2 simplex.
Exactly, the same identification as before. And again, the old gap now occurs here. Why doesn't, there's the cursor. The old gap appears here in front of the Vj, therefore this new gap doesn't sit at the jth spot in this hull, it sits at the j minus first spot, because we already left out one beforehand. This is what explains the sign. And now you can guess, next step is I distributively pull the sum back inside these two summands. So I write this now as sum I equals 0 n, sum j equals 1 to I minus 1. And then these two signs, this one and this one, I can write them as one sign by just adding the exponents. And then I get sigma n defined on this singular n minus 2 simplex. Right. And now I pull this sum, I pull this sum here inside this one here. So I will get the new exponent minus 1 to the I plus j minus 1. And let me just take this minus 1 out of this product of minus 1 and instead write a fat minus here in front of the whole thing. So in that case, I get I equals 0 to n, j equals I plus 1 to n minus 1 to the I plus j, and then the n minus 2 singular simplex given by V0. First leave out Vi, then leave out Vj, and then go up to Vn, and that's it, right?
Can you scroll down to see maybe the whole equation
thing,
somehow?
yes. So
maybe a bit further.
Well, the important part is here, so yeah, I think this is as far as I can go.
For a moment at least, yeah.
Yes, yes. Well, I can zoom out if you want. Maybe not.
Better not.
Maybe not, yeah. Okay, so now I claim, of course, that these two sums we've got here, so this line, where's the cursor? This line here cancels out with this line. Yeah? So I claim that the same summands occur in both. So why is that true? Well, what happens in the first sum? I goes from 0 to n. So sort of the second gap is the one that fixed, but that can be arbitrarily from can sit arbitrarily between V0 and Vn. Any of those is possible. Then comes the second gap. This now goes from j equals 1 to I minus 1, which is saying the jth one is before the ith vertex. Yeah? But if you first put in Vi at an arbitrary spot, and you're allowed to put in Vj at any spot before that, then this actually lists all possibilities of taking out two vertices out of this convex hull. That's simply all possibilities you can possibly get. And actually in the lower part, the same thing happens, except that sort of the pivot is now the other one. Yeah? So we sum again from I equals 0 to n, but it's the first gap that we choose first, which can be arbitrarily assigned between 0 and n. And afterwards, we're allowed to still assign the second gap at any place behind this first freely chosen gap. And of course, that's another way of constructing all possibilities to take out two vertices from this convex hull. So precisely the same singular n minus 2 simplices occur in both those lines, and the first line is subtracted by the second line, which means we end up at 0. Okay. So this is the proof of the lemma. This is the formal argument for this, for what geometrically should be more or less apparent. And yeah, with this definition of the boundary homomorphism and this proven lemma, let's collect now what we've gathered so far. With any space X, we associated what's called a chain complex. And that's a definition right away, so let's put it in green color again. We associated a chain complex which by definition is just a sequence of, in our case, abelian groups. So there is a sequence of abelian groups, which in our case are just the chain groups, the singular chain groups we have just defined. And all these are connected by homomorphisms, which in our case are the boundary homomorphisms. So this is dn plus 2, I guess. The index alludes to where the boundary operator starts. So that's dn plus 1 going to Cn sing x. And then we got yet another boundary operator dn ending up in Cn minus 1 sing, and so on and so forth. And now a chain complex is not only such a sequence of abelian groups connected by homomorphisms of abelian groups, but the decisive additional property is that dd equals 0, so that going along two successive boundary maps gives 0. So a sequence of homomorphisms of abelian groups, in our case, if it's a chain complex of abelian groups. Such that the chain complex property, so such that dd equals 0 holds. Yeah, so going along two consecutive boundary maps gives 0. Okay. So if we now got such a chain complex, then we can associate two new notions with it, namely the ones about boundaries and cycles. So first of all, Bnx, that is supposed to be the image of the n plus first boundary operator. And all elements in this subset, so it's a subset of the nth chain group. Somehow I don't have a pointer here anymore, can I? Ah, yeah, there it is. So it's a subgroup of this nth chain group, and it's called, I better say the elements of it are called the n boundaries. And likewise, we define Znx as the kernel of the nth boundary map. So this is again a subgroup of this nth chain group. Yeah, so all elements, all n chains, all singular n chains here, which are mapped to 0 by the nth differential, by the nth boundary homomorphism. And these are called the n cycles. And maybe you stumble over the terminology Z here, but that's actually because the letter C, as in cycles, is already taken because, well, C is reserved for the chain groups. So that's why even in the English literature, the letter Z is used, sort of borrowing from the German word Zykel. So this is why this is usually abbreviated with a Z instead of a C. Okay, so these are both subgroups of the nth chain group. And now the point of the chain complex condition dd equals 0 is that, so let me write it down directly. The point of this condition is, well, if I have applied the n plus first differential and then I apply dn again, I get 0, well, that means that boundaries, yeah, namely elements in the image of dn plus 1, are mapped to 0. In other words, they do lie in the kernel of dn. In other words, there are cycles. So this condition just means that every n boundary is an n cycle. And homology now measures the defect as to whether the converse is true, whether also every cycle is a boundary or not. And that's precisely going to happen if the homology is trivial, and otherwise it's not going to happen. So this gives now our definition we have been striving to give. Definition: the nth singular homology group of X. Oh, that's a definition, so I should put it in green. Let me write it out first. Whoops. Color green. Okay. The nth singular homology group of X is Hn, and again we write the upper index sing to refer to singular homology here, but we can also leave it out at some point. This is now given by the quotient of all cycles, so let me write it in detail, of all n cycles mod out all n boundaries. Yeah? So the chain complex condition gave that actually boundaries form a subgroup of the cycles, and now the quotient group, that's what's singular homology.